Alright guys, so here's the Unit 2 review packet, and we finished the unit on Thursday, so I am going to go ahead and go over your packet, your review packet with you, so we can have a pretty good review of the entire unit. So I'm not going to do every single question, but I will go, I'll go around doing some of the questions. I was going to do number 1, but it seems like there's only 2 functions, a linear and then a quadratic. Felt like that was a little bit too easy. I'm pretty sure you guys can handle that. I will do question number 2, and then you can go back and see how I did it, and you should be able to do number 1 with much easiness than this one right here, number 2. So number 2 says state the open interval on which the function f, is increasing. Okay? So remember, we want it open, and every time there is an interval, we are talking about the domain. Okay, so we look at the x values, and we look for where this function f is increasing. So I know it's open, so I'm already going to put a parenthesis, okay? So I don't forget. It looks like here is not increasing nor decreasing, it's just constant. And then it decreases right here on this little interval between 1 and 2, it is decreasing, but then it hits a bottom over here, and then it stops decreasing, and it begins increasing. So from 2 to a 3, the function is increasing. So I can say from 2 to 3, the function is increasing. But then from 3 to 4 is also increasing. It's just increasing a little higher. Started from 0, went up to 2, and now went up to 4. So I can actually say from 2 all the way to a 5 is increasing. Okay? So I can actually switch this and say all the way to a 5 is increasing. From 2 to a 3, and then all the way to a 5 is increasing. Okay? So that's an increasing interval. It went all the way to a 2, and then all the way to a 3. And then from here, it starts decreasing values. So. And then it says state the open interval, so I'm going to put parentheses because it's open, on which f is decreasing. Okay, again, we read it from left to right. And over here is constant, and then right when you hit x equals 1, if I cover anything before that, I see that the function is decreasing. So from 1 to 2, from 1 all the way to x equals 2, the function is decreasing. We already established that from 2 to 5, it is definitely increasing, is going up. And then from 5 all the way down to 9, the function, so from 5, x equals 5 to x equals 9, the function is decreasing. And then it says state the domain and the range of the function. So the domain is from x equals -4. We have a closed dot, so I'm going to put a bracket, -4, and I'm still talking about the domain. This function is continuous all the way to a 9, and we will also use bracket because it's a closed dot. Okay, so I was talking about the domain, so I looked at the x values. Now I'm going to talk about the range. On the range, I'm looking at the y values of the function. It looks like the smallest y value is 0 right here at this point, and is included, so I'm going to use a bracket, 0, and if I frame it, my function stops at a 2, a little bit higher, stops at a 3, so it goes all the way to a 3. Okay, so if I want to see range, I frame my function from on the y values, and that's what I look at it from 0 over here all the way to a 3. Okay, there is our range. Now state the coordinates. Now we're talking about an x, y pair. State the coordinates of any relative minimum. Okay, a relative minimum. So it was constant, and then it decreased. Right here it hit a relative minimum, and then it went up. So 2, 0 is a relative minimum, and then it kept on increasing and increased even higher, and then it started decreasing, and it stopped right here. This is not considered a relative minimum because we did not have a change in the slope. Okay? And then it says, state the coordinates, again, we're talking about x, y, on any relative maximums. So it was constant, we decreased, found a minimum value, we increased much higher, and that is the relative to what is going on here. We found a relative maximum at 5, 3. So we have a 5, 3 is a coordinate pair of a point that marks our relative maximum. And this guy over here is our relative minimum. Relative minimum, okay? Now it tells us write a piecewise defined function. So we need to define the domain. It says there's 3 of them, so I better be able to see 3 of them. And we need to define the domain. All right, so piecewise defined function always start with the f of x on the outside, and there's 3 options. There's 3 functions. I like to go ahead and make a line over here, another one, and another one. I like to label them and decide where they live. From -4, if, and if, okay? If you're talking about -4, all the way x values, all the way to a 1, we have our constant, our linear constant, and that is y equals 2. I already have the y equals outside, I don't have to write it in here. So y equals 2 between -4, including -4, all the way to a 1, including a 1. You can put the including in here, okay? Between a 1, since my 1 is already included up here, I'm not going to include it down here. Between 1 and 3 over here, between 1, all the x's between, oops, I should not have put that there. Between 1 and 3, I'm going to include the 3, we have our parabola. I'm going to write parabola or quadratic. Okay? And parabolas is always x minus an h squared plus a k. Let's go ahead and find our h and k value, which is our vertex of the parabola. It happens to also be the relative minimum of this graph at 2, 0 right here. So 2 for x and 0 for k, but I'm not going to write a 0. And I just put in the positive 2 value in here, but because of the negative that is part of the formula, it turned into a -2. I need the stretch. I need the a value that goes in the front. I come back over here and I count from my vertex to the next point on my graph. It looks like we are rising 2 and running 1. So I rise 2 points and run 1. Because my run is a 1, and it gave me a whole number of rise 2, run 1, because the run is 1, it's a whole number, I can go ahead and count that stretch of positive 2. Okay? The last thing I need to see, they said is 3 pieces. I saw the constant, I saw the parabola. Now the last thing I see is a linear absolute value. In the linear absolute value, we do have an absolute value, x minus an h, and the k goes outside. And that function is between the 3, I already included the 3 here, so I will not include it here, is between, all the x is between 3 and all the way to a 9, including the 9. Okay? And let's go ahead and find our h and k, which is 5, 3. 5, 3, which happens to be the relative maximum of the function. So 5 for x goes in here, positive 3 for my k goes here. Let's take a look at the slope for this absolute value. So from 5, I would have to drop down to a, from a 3, I would have to drop down to a 2. So I drop down 1. And I run 1, 2. So drop 1, run 2. That means drop 1, run 2 is -1/2 for my slope for the linear absolute value. And there we go. Okay. So once you understand that we're always looking for a starting point or vertex and a slope, Here's the starting point or vertex and our stretch, and this just happened to be a constant, a linear constant. So that is how we take care of this problem. You will be able to do the previous problem over here, number 1, with the same knowledge that we used over here. Okay. Now question number 3. Question number 3 says, let me zoom this just a little bit more, see if it makes it any better. Here we go. All right. Question number 3 says, graph f of x and g of x on the same set of axes. Let me also grab a different color pen here. Let's try this one. Okay. So graph f of x and g of x on the same set of axes. Use the graph, and then so we use the graph to look at our solutions, but we also going to do it algebraically. Where does these two functions meet each other? Okay, where do they equal each other? So let's go ahead and take care of f of x first. F of x, let me just write it separately. F of x is 3 times the absolute value of x plus 1. Let me go ahead and take all the information I need out of this function. I need the starting point. The starting point is opposite here, same of what is outside. There's nothing out here, absolutely nothing. So opposite of positive 1 is negative 1, same as 0, there's nothing there, is 0. Okay? And then the slope, because it's a linear absolute value, is this value right in the front. Rise 3, run 1. So we'll go to negative 1 for x, 0 for y. We're going to rise 3, 1, 2, 3, and run 1 to the right, and its reflection to the left. So there is my absolute value, my linear absolute value function. And then I finish graphing f of x. Now g of x is just this line 6. Okay? In other words, is y equals 6. We're calling this the g function, the g of x function. So y equals 6 would be up here. 1, 2, 3, 4, 5, 6. It would be right here. Let me use this color right here. Okay? All right? Right there. Oops. Okay, so this is my g function, and the red one is my f of x function. It looks like they roughly meet somewhere here. It's really hard to tell. Okay, maybe at a 1. Looks like they meet at a 1. But I think I might have messed up over here on my slope. Up 1, 2, 3, over 1. Yeah, I might have not found a precise cross over here. And that's why we need to do it algebraically. So we know for sure where these two functions are meeting each other. To solve it algebraically, I will grab the f of x function and set it equal to the g of x function. The f of x function is 3 times the absolute value of x plus 1. Equals the g of x function, which is just 6. To isolate the absolute value, we're going to divide both sides by 3. We're going to get the absolute value all by itself. The absolute value of x plus 1 equals 2. At this moment, the absolute value is all isolated. It's time for me to use the definition of absolute value. It tells me I can take the expression out. X plus 1 equals 2. And I can also take the negative version of the expression, negative 1 times the quantity of x plus 1 equals 2. Okay, it's those little flashcards we made. Hopefully we don't need them anymore. Here we can simply solve it. We subtract 1, and we subtract 1 from both sides. We get the x equals 1. So there is one of the solutions, and I was able to find that graphically, that at x equals 1, they do meet over here. Then over here, we're going to divide by a negative 1, divide by a negative 1. You're going to get x plus 1 equals negative 2. And then we subtract 1 on both sides. We get the x equals negative 3. So I couldn't quite tell, is because I probably messed up on my slope over here. It should have gone up here and met on x equals negative 3. Negative 1, negative 2, negative 3. So I think I messed up on my graph right there. And that's why it's nice to see it algebraically, so we can make sure we did it nicely graphically. Okay? So these two methods should match with the same values. The x equals 1 and x equals 3 is where they meet. These two functions meet. All right. Now let's go ahead and solve a couple of the inequality, a couple more absolute value functions. Solve the following absolute value equations. It is an equation, just like we were doing over here. So I'm pretty sure you can do them using the same knowledge we used over here. I'll just do one that has something to do with fractions, because that's one of the students' scary aspects of mathematics is when it comes to fractions. All right, and then we are graphing our solution on a number line. So I try to point out everything I need to do here. I must isolate the absolute value. Isolate, isolate, isolate. That's the magic thing here. I got to isolate before I can use the definition. So there's a -1 here. I can divide by -1 or multiply by another -1. Here we go. Multiply by a -1. -1 times -1 is +1. Now I'll have my absolute value of x over 2 minus 5 equals -4. Okay? It's the same thing as saying divide this by a -1 and divide this side by a -1. Now, the absolute value of anything, it doesn't matter what real number you plug in for x. It could be a 0, a -100, a +100. Anytime you take the absolute value of something, it will always be positive. And a positive number never equals a negative. So this is definitely a no solution situation. Okay? So because anything out of the absolute value will always be positive, does not equal a negative. Let's go ahead and solve another one with fractions, because we really didn't get a chance to touch that fraction in there. And that would be number 6. Anytime I want to get rid of a fraction, we always multiply by the reciprocal. So I'm going to go ahead and multiply by 5 over 2. But if I do it on the left, I better do it on the right. 5 over 2 is the reciprocal that we need to multiply by on both sides. Then we go ahead and just 1 second. Give me 1 second there. I was just answering a text message. Sorry. So this multiplying by the reciprocal over here will cancel. Okay, it doesn't cancel. It's abuse of the word cancel. It becomes a 1, and 1 times the absolute value is 3x plus 2. Over here, we can simplify it before we multiply it, or you can just multiply it and divide it. 20 times 5 is 100, and 100 divided by 2 is 50. I would rather much simplify it. Divided by 2 here, divided by 2 here, we get 10. And 10 times 5 is 50. Either way, we get the answer 50. E equals a positive, so we're good. Let's go ahead and use our definition of absolute value, because the absolute value is completely isolated. We take the 3x plus 2, set it equal to 50. We take the negative version of 3x plus 2 and set it equal to 50. I am going to stop here because I'm pretty sure you can take it from here. I just wanted to give you a head start on how to get rid of that, that fraction. Okay? All right. Now let's solve the following inequality. We have to remember those rules of inequality, especially the most important rule of inequality is to, if we divide by a negative, we need to flip or switch the inequality. Okay? Let's go ahead and go over here, number 9. Let me give you a head start on number 9. I want to get rid of a fraction, just like number 6 previously. I will multiply by the reciprocal, including the sign. That would not be the reciprocal if we did not include the sign. So negative 3 over 2. Over here, also by a negative 3 over 2. Now, the negative 3 over 2 times the negative 2/3 becomes a 1. My absolute value is all by itself of x plus 4. I multiplied by a negative. I better flip the inequality. And I will simplify it by 2. Simplify it by 2, we get a 3. And 3 times negative 3 is negative 9. Now, the absolute value always yields a positive number. And a positive number is always greater than any negative value. Positive number greater than a negative value, always. So this is going to be all real numbers. So all real numbers, doesn't matter what you plug in for x. You could plug in for x a negative 1,000,000. And if you take the absolute value of a negative 1,000,004, it would still be positive and it's greater than a negative 9. So I want you to see the use of the reciprocal, a negative reciprocal, and the knowledge that I always stop and think to myself, this is always positive, and then we make the decision if we need to go on or not. Okay? To show the solution on the number line, I would just show, here's my number line, here's 0, I want all of it. Okay, those are all real numbers, from negative infinity all the way to positive infinity. We want all real numbers. Okay, all right. Let's go ahead and see if we can do a few more problems here. How about number 12? How about number 12 over here? Number 12, let me see, I might need more room, so I'm going to put this paper here. Okay, not number 12, number 11. Okay, number 11 says I have a 2 plus the 2 times the absolute value is greater than or equal to 0. So we have a greater case, and we need to isolate first. Isolate, isolate, isolate. So let's go ahead and subtract negative 2 from both sides. When we subtract 2 minus 2, we get 0. We end up with just the 2 times the absolute value of x minus 5. Is greater than or equal to 0 minus 2 is negative 2. I need to continue. I need to isolate more. So let's go ahead and divide it by a negative 2. I'm sorry, divided by positive 2, divided by positive 2. Then a 2 divided by 2 is a 1. 1 times the absolute value is the absolute value of x minus 5 is greater than or equal to a negative 1. Again, I shouldn't have done that question because it gave us same as before. The absolute value of anything is positive, and that is always greater or equal to a negative 1. It's not equal, definitely not equal, but it is greater. And because it is greater, it is all real numbers. Okay, same case as before. The positive values is greater than negative 1. So we're done here. All real numbers on the number line would be a 0, and everything in here from negative infinity to positive infinity. And some of you might say, but Mrs. Myers, a positive is not equal to negative 1. I know, but the inequality is saying the value is greater than or equal to. It's not equal, but it is greater. So it's all real numbers. All right. Let's go ahead and do, let's see what we have here. How about over here on the other side, we have graphing systems of inequality. Let's do some graphing inequalities. We have 2 functions here. We have the y is less than or equal to 4. On this case, I have to make a few decisions. If it has a equal, it's going to be a solid line, a solid graph. And because it's a less than, we're going to shade below. And this is just a linear function, y equals 4. So I'm going to go to 4. 1, 2, 3, 4, right here. And because it's solid, we already decided that. There's my solid line. And I'm supposed to shade below because it's a less than. I'm going to barely make a little bit of a shading here. Not much. Just to give me an idea. Let's move on to the next one. We have a y is greater than x. Because it does not have the equal, we're going to just dash it. It's a dashed graph. And because it's greater than, I'm going to shade above. And the y equals x line is this very classical graph over here. It is this diagonal right here is dashed. So there we go. Here's my dashed line. Because it's the y is greater than x. If you think of it, the y equals x is just this diagonal line right here, but we want it greater, so it's dashed. And I'm supposed to shade above. I would shade above. Now I know exactly where they're meeting. They're only, the shading of the both functions is only meeting right here. So I can pick any point in this shaded area and it will satisfy both of these functions over here. Okay? So you will be asked on the test to pick points. You have to pick anything in the shaded area. There's infinitely many options here in the shaded area. Okay. Let's do something that is not so simple. Let's do something like number 16, an absolute value and another absolute value. All right, so we have over here, just like we were graphing before, opposite from x is -2, and same as outside is 0. So I'm going to go to -2, 0. -2, 0 is right here. I'm going to use the slope of up 1, run 3. Up 1, run 1, 2, 3 to the left, and his reflection to the right is 1, 2, 3. It is supposed to be a solid. I forgot to make my notes. It's a solid and solid graph, and I'm shading below because it's a less than, so below. So I'm going to do a solid graph right there. And I'm going to do barely a little shading because I'm going to try to find where both of the shading are meeting each other. Not much. Now let's go to the next one. It is a solid as well. Solid graph. And I'm going to be shading above because it's a greater than above. Let's go ahead and take a look. There's nothing being added or subtracted from x, so that's 0. There's nothing on the outside being added or subtracted, so that is also 0, 0. So there's 0, 0 right here. The slope is drop 1. The slope is drop 1 and run 1 on both sides, and his reflections right here. It's solid, so here we go. And here we go. But I am shading above the actual graph. So I will shade above. Now I see exactly where both of the shading meet, right in between these two absolute value functions. And there we go. So I can pick any point. I can pick over here 3, 4, 0. I can pick -7, 0. It will be a good point that satisfy both of these equations, not equations, inequalities. All right, let me just do 2 more, and I'll try to keep it a short video, not too super long. Let's go ahead and do number 18. It is solve for x. I'm trying to get x all by itself. So I'm going to be using PEMDAS. PEMDAS backwards, so I can isolate for x. But then there's also a bunch of other things here that we learned in this unit. Quadratic formula, factoring, and solving by square roots. So there's 3 methods. The 3 methods of solving for x. And I have a video covering those 3 methods. When I look at this, I am not going to do factoring because it is not of the form of ax squared plus bx plus c. That's when I try to factor something. This looks like I have something squared. I'm going to be probably using the square root so I can undo the square. But first, I need to isolate the square quantity. I'm going to subtract 15 from both sides. We get 3 times x minus 2 squared equals 75. Then I'm going to divide by 3. I'm still working on my PEMDAS to isolate the squared quantity. Divided by 3 on both sides. We get x minus 2 squared is 25. Then I'm going to definitely use the square root function on both sides, on the left and on the right. The square root function will undo the square, And by definition, the quantity inside comes inside the absolute value. X minus 2 equals the square root of 25 is 5. And from here, you're going to set up your two equations using the definition of absolute values that we just did a few minutes ago. So I wanted you to just see how we isolated and got to this point. So please continue from here. To be continued by you. Over here, last one, number 21. I look at it and I say, oh, I have a square item. It kind of looks like this right here. I just have to put things in the right order. If I subtract 14x from both sides, I'll have 0 equals, let me rewrite it in this correct form right here. The square terms always come first. So I'm going to get my negative 3x and write it first. And then my coefficient that multiplies the x should come second. That would be my negative 14x. And my constant always comes last. And the only constant we have here is positive 24. Then we look at it and I say, is there anything I can factor out? Because factoring, quadratic formula, or square rooting are the things that you should always keep it in our minds. 3 is divisible by 3, but 14 and 24 is not divisible by 3. But I certainly can factor out a negative. I do like my leading coefficient to be positive. It makes guess and check much easier. So you know what? I can divide this by a negative 1, this by a negative 1, and this by a negative 1. So 0 is going to equal negative 1 times, now the 3x squared is going to be positive. The negative 14 is also going to be positive 14x. And the only thing that's going to be negative is my constant in the back. And that is okay. All right. So now I have 0 equals negative 1. I just have to factor these two things right here. I am going to go ahead and use a piece of paper because we are running out of room over here. So let me rewrite it right here. We have 0 equals negative 1 times 3x squared plus 14x minus 24. Remember, we factor out the GCF, but we must keep it right here. We don't throw it away. Okay? Nothing in mathematics. You factor it out, you need to keep rewriting it because it's part of your function. It's part of your equation there. So let's use the guess and check method. 3x times x, when multiplied, these two factors gives me 3x squared. Negative 24, there are lots of factors. Okay, 1 times 24, but to give me a negative 24, one of them has to be negative. Let's go with negative 1 right now. We have 2 times 12, maybe negative 2 times 12. We have 3 times 8, so maybe negative 8 times 3 gives me negative 24. And the last thing, negative 4 times 6. All those are options. Let's just play with a few and see what we get. 3x takes preference right here on the beginning. Remember, whatever we put in here multiply, and here to multiply, you gotta add up to the middle term of 14x. You gotta add up to 14x. I'm gonna do some mental math first, just to play with numbers here. If I put a, 24 is too big, okay? 24 is too big to put it here on either way, so I'm gonna cross that one out. If I put 12 here, positive 12, it gives me 36, and negative 2 would give me just a negative 2. That is way too big as well. Even if we switch it around, it still doesn't give us what we need. If I put a negative 3 and an 8, if I put an 8 here, that would be an 8x. If I put a negative here, would be a negative 9. That doesn't work. Let's try this one. Hopefully this last two will work. If I put a 6 here, 3 times 6 is 18, and negative 4 times x, that might work. Let's try it. If it's not, we'll fix it. A positive 6 here, a negative 4 here. Negative 4 times x is negative 4x. 3 times 6 is 18x. When we add this 2, we get 14x. So there we go. And our factoring is this value right here. But remember, from the beginning, I'm going to come back over here, is 0 equals -1 times the 3x minus 4 times the x plus 6. Those are all the three factors from our original equation. Now to solve for x, I'll set every single one of these three factors equal to 0. -1 equal to 0 makes absolutely no sense. Now I can throw that GCF away. 3x minus 4 equals 0, and we have x plus 6 equals 0. So we have, I didn't really throw the GCF away. I'll take those words back. I'm not solving for x here. The GCF does not have an x variable for me, so I really don't need to worry about. Maybe that's a better explanation. Here I do have an x variable, and that's what I'm trying to solve for. So add 4 to both sides. We get 3x equals 4, and divided by 3 on both sides, we get an x equals 4/3. That's our first solution. Then subtract 6 from both sides here. We get that x equals -6 is our second solution. All right, so that was problem number 21. I ran out of space over here. I kept on factoring. I continue on the other page, and we were able to solve for x. Okay? So I'm pretty sure you can do the other questions here, just to give you a heads up, to help you a little bit more. This is very similar to number 18, and this is also very similar to number 18. 19 and 20 is very similar to number 18. Number 22 and 23, you are probably going to be doing the same thing I did here with number 21, factoring or using quadratic formula to solve for these ones. All right? So good luck. Finish your review. Ask me questions. Come ready to ask questions on Monday, because your test is next week. Have a nice weekend. Goodbye.